Okay. Hello everyone, welcome to my master thesis defense presentation. My name is Selahattin Can İnal and my supervisor is Professor Serhan Özdemir. My title is, as you see, Modeling of an Impact Resistant Navigation System for gun projectiles based on low-cost MEMS sensor. And I'm going to advance according to this outline. In brief, I can group my thesis under three main sections: the navigation system design, CFD analysis, and shock survivability of electronic components. First, I want to introduce you the guided projectiles. As you see, guided projectiles has control surfaces on the airframe of the projectile body, and their first combatant examples were used in 70s during Vietnam War. And we can classify guided projectiles under two main categories: fin stabilized and spin stabilized guided projectiles. Fin stabilized guided projectiles are more similar to a missile. They have larger control surfaces, and their airframe is completely different from the regular projectile shape. On the other hand, the spin-stabilized guided projectiles has smaller control surfaces only at the nose part of the munition, only at the fuse part of the munition. And this part is spin decoupled from the rest of the munition body. And as you guess, there are some advantages and disadvantages of both groups. The biggest advantage of the fin-stabilized guided projectile is the enhanced maneuverability due to larger control surfaces. On the other hand, spin-stabilized guided projectiles are widely used because a regular conventional projectile can be easily upgraded, only modifying the fuse of the munition. And now I want to show you a comparison of a guided projectile and a regular conventional projectile. This M795HE is a standard regular projectile, and its CEP, circular error probable, is almost 200 meters. On the other hand, a guided projectile accuracy is about 20 meters, and its cost is not too much. In the figure right, you see a comparison of CEP, the same desired effect achieved by only using 3 Excalibur rounds. This is a guided projectile.
That's an impact radius, right, John?
Yes, yes.
That's a neighborhood. Okay, it's not very clear, but it's a neighborhood, and those yellow circles or ellipses are the impact radius.
This shows that we are aiming this red square, and when we fire 3 Excalibur round, it drops here, approximately. But instead of, if we use a regular projectile, we have to fire 147 conventional round to achieve same effects in this area. Okay, now I want to tell something about guided missiles and guided projectiles also. If operational conditions are suitable, guided projectiles can be used instead of guided missiles also, because they are very cheap when compared to a missile, and they do not, however, they do not carry huge warheads. They only carry a few kilograms of warheads, and their ranges are not as much as a missile. They do not have thousands of nautical miles. They only have, in maximum, 30 or 50 nautical miles. But you can store thousands of guided projectiles in your arsenal because their sizes are very small. And one of the biggest advantages of a guided projectile is that you cannot stop an incoming projectile because their radar cross-sectional areas are very small, and most of the projectile has a supersonic flight regime. Therefore, even you detect an incoming projectile, you do not have any time to react. On the other hand, there is lots of countermeasure techniques for guided missiles. Now, I want to talk about guidance methods. As you see, we can group guidance under two main categories: self-contained guidance systems and guidance systems that use man-made electromagnetic device. In my thesis, I use preset guidance method. I planned a guidance path, as you see in the figure 10. The munition will start an initial flight altitude, and it will make 5-degree pitch up for 5 seconds, and then it will cruise for 10 seconds. After that, it will descend with 5-degree flat path angle for 5 seconds. This is a mid-course guidance. It will be a mid-course guidance simulation. In preset guidance, the entire flight path is loaded into the munition computer before the launch, and flight computer counts the time and alters the flight path according to prior information. And even though the preset guidance is the most basic guidance methodology, this guidance method is widely used even with many latest high-tech weapons, because the preset guidance has utmost stealth capability. You do not emit anything. You do not give your enemy to catch your munition. Therefore, I want to make a simulation for preset guidance. Now I will continue with dynamics of the projectiles. We can separate dynamics into two groups: longitudinal dynamics and lateral dynamics. In longitudinal dynamics, we have two force, lift and drag force, and one pitching moment. And in longitudinal dynamics, our munition moves in the x and z axis and makes a pitch angle. As you see in the formula, there are some coefficients, CL, CD, and CM. These are lift, drag, and pitching moment coefficients. They are dependent to angle of attack, pitch rate, and fin deflection angle. Now I want to talk about lateral dynamics. In lateral dynamics, we have one force and two moments: side force and rolling and yawing moments. And we have also some coefficients here, and they are also dependent to side slip angle, rolling and yawing rate, aileron, and rudder deflection angles. These aerodynamic coefficients are determined by CFD analysis, wind tunnel test, and live flight test. Now I want to show you my control input combination for basic fin reference projectile. My aileron command is fin number 2 in positive direction and fin number 4 in positive direction. My rudder command is fin number 1 in positive direction and fin number 3 in negative direction. My elevator command is fin number 2 in positive direction and fin number 4 in negative direction. This is my control input combination for basic fin reference projectile. And this is the complete equations of motion for 6 degrees of freedom for a projectile for any aircraft. As you see, the most of the terms are Euler angles, and the most critical parts are Cy, Cx, Cy, Cz, etc. These are aerodynamic stability derivatives. These are combination of lift, drag, and yawing moment coefficients. These coefficients are specific to any munition. As you guess, the parameters of ammunition is confidential for its manufacturer, and actually I use a basic fin reference projectile in my simulation because some of its aerodynamic stability derivatives are given, such as rolling moments coefficients. However, some of the parts, some of the aerodynamic stability derivatives are missing. Therefore, I could not derive these functions for a basic reference projectile, and I use a guided missile state space model instead of a basic reference projectile. This is a state space model which is published by Raytheon engineers for a guided missile study. It has a similar flight regime with a guided projectile around a thousand of meters per second. And in this state space model, I have two states, angle of attack and pitch rate. And my control input is elevator fin deflection angle. And there is also some assumption. First of all, this is a linear model, and lateral forces and moments are neglected. It means that the munition is moving in the x-axis and changing its altitude, and makes a pitch angle. The munition has no any rolling or yawing angle, and the projectile body is rigid. The weather conditions are also constant. There is no disturbing effect. Now I want to show you the open loop response of the system. This is my block diagram for an open loop system for a standard AX plus BU state space model. This is the step response of angle of attack. You see a pitch down and pitch up motion for a given step elevator input. This phenomenon is named as pugoid mode. Let me explain pugoid mode more clear. In the first state, there is a given elevator deflection angle, and the munition starts to descend. After a while later, velocity of the munition increases, and lift force overcomes the gravitational force. As a result of that, the munition starts to ascend. And after a while later, the velocity of munition becomes less than the initial velocity, and the gravitational force overcomes the lift force, and the munition starts to descend again. This motion continues by a specific time. And this is the step response of the pitch rate. As you see, the motion of the munition becomes less by time. And now I want to continue with full state feedback controller. First, I will design with a controller with pole placement method. I determine my design criteria as you see. Damping ratio is 0.65, settling time is 0.4, and natural frequency is 15.38. I determined this criteria according to prior studies on guided projectiles and guided missiles. And this is the locations of open loop and desired poles. And before establishing a controller, we have to check its controllability and observability. As you see, both matrices are rank 2 matrices. Since I have only 2 states, it means that the system is completely controllable and completely observable. I can continue to calculate the feedback gain. I use Ackersman formula to calculate the full state feedback gain, and this is my desired characteristic equation, and my full state feedback gain yields to these values. And this is my block diagram for full state feedback controller. As you see, there is a simulation block. In this block, let me show you this block more clear. In this block, I have a flight gear animation simulation block for in MATLAB Simulink. I use flight gear with MATLAB to visualize the simulation. In this block, I have to supply latitude, longitude, and altitude, roll, theta, the pitch angle, and yaw angle. And I have to convert the x, y, z position to latitude, longitude. I use flat earth to LLA block, and I also supply the artificial horizon indicator and altitude indicator using state variables. You can observe the motion of the munition in here. Now I have a small video of this simulation. This is my 3D model munition. I use Flight Gear open source simulation software for this simulation. Now the simulation will start. Now it will make 5-degree flight path angle, and it will cruise with 0 pitch angle, 0 flight path angle, and it will descend. Yes, you can also observe from here, from the artificial horizon indicator. Yes, as you see, the response of the system is quite sharp because I did not penalize the effort of the system. In LQR controller, I will give a penalizing matrix for control input, and you will observe this quite sharp response will be smoothened. And this is the outputs of the system. As I told you, these are quite sharp, quite quick movements, and you can see that the system tracks the flight path commands quite well. And now I will continue with LQR controller. And in LQR controller, we have a penalizing cost function which has Q and R penalizing matrix for error in the states and control input effort. And I solve Riccati equation for the given Q and R matrix using LQR command in MATLAB, and I calculate the feedback gain using these penalizing matrices, and my LQR gain yields to this value. My block diagram is same with the pole placement method. This is the same block diagram for LQR controller. So the only changing is the K full state feedback gain. Let me show you the simulation of the LQR controller. You can also observe from the motion in here, from the indicator here. Yes, it's ascending. As I told you, the output becomes less quick, less sharp, because I penalize the effort. Now it's descending and returns to initial flight altitude. That's all for LQR controller. And this is the outputs of the system. These peaks are smoothened because I penalized the output. And the same effect can be observed for state variables also. For same penalizing control input effort, I penalize the pitch rate response by 100. As you see, the overshoot becomes less and settling times becomes longer for the first state. And I also designed an observer because, as you see, as you know, we cannot measure every quantity in our system. The noise can be high, or the sensors may not be placed in our system. Therefore, I want to make an observer. However, in my state space model, I have a C matrix 2 by 2, and the inverse of this controllability observability matrix does not occur because the control observability matrix is not becomes a square matrix. Therefore, I use only pitch rate output for the observer design, and I check the observability of the system again. As you see, this is again a rank 2 matrix. It means it's complete observable. And I placed observable poles 2 times faster than the controller to converge fast enough. These are my locations of the observer, and my observer gain yields to this value. And this is my full state observer block diagram. Actually, this is the observer is a duplicate of the system. In here, I observe states and estimated states and the error. And as you see, the observer converge to a plant quite well. I start the plant and observer with different initial conditions to observe the convergence. And this is the error convergence of the system. And almost 0.3 seconds later, the error minimized. And now I will continue with CFD analysis of the basic finite reference projectile. I use ANSYS Fluent academic software for the CFD analysis, and I calculate drag, lift, and pitching moment coefficients for 40 meters per second flight velocity. Because some of the parameters are already given in the literature, but for supersonic flight velocity, for a small size lab experiment, a supersonic flight velocity is an inaccessible level. Therefore, in future life tests, the catapult or airgun systems can be used for this model. Therefore, I want to calculate these values to light up the environment for low velocity launch systems. Therefore, I calculate all of these coefficients for 40 meters per second flight velocity. And I calculate each coefficients for 0, 2, and 4 degree fin deflection angle. I use RANS-based K-epsilon turbulence model. Why? Because first of all, my flow is turbulent around projectile because its Reynolds number is greater than 5 times 10⁵, and actually there is lots of turbulence models such as direct numerical simulation or large eddy simulation. Because of less computational time, I use K-epsilon RANS turbulence model. And these are my boundary conditions. This is velocity in net, and there is outflow. And I place the outer diameter of the environment as 15 times of the projectile diameter to do not disturb the flow around the projectile. This is the outer mesh, and I increase the mesh around the projectile to obtain more accurate solution. And in total, I create 511,139 mesh elements because academic software of the Fluent allows maximum 512,000 mesh elements. This is the maximum number that I can achieve. And before conducting CFD analysis, we have to check mesh independency of our boundary conditions. As you see, I decrease the mesh number, and my relative error is also increased, but not too much. As you see, the direct coefficients are quite same, 0.14. It shows that my boundary conditions and model is correct. And this is the calculated aerodynamic coefficients for 0, 2, and 4 degree tail angles. And these are the flow around the projectile frame. This is the contour demonstration of the flow. you can observe turbulence around the fins, and you can observe the vector distribution around the fin. Now I will continue with shock survivability. This is another important issue for a guided projectile, because an artillery firing environment can create hundreds of thousands G within microseconds, and guided projectiles has many electron components in their computers. Unfortunately, in the literature, there is very limited source for ruggedization applications for projectiles or for any munition. But as you may consider, the giant weapon developers have already this knowledge for themselves.
It must be the military reasons, Jambi, right?
Yes, of course.
It's a military secret.
Yes, because of some confidentiality issues. And I use Hopkinson bar test equipment to reach thousands of acceleration within microseconds. And I prepare 5 specimens, 3 of them made up with SMD components, 2 of them made up with THD, larger and heavier size components. And I use only commercial off-the-shelf components. These are my list of components. I want to take your attention to one of my components, the MQ6050. I did not use this accelerometer to measure the acceleration during the impact, since its maximum acceleration range is only 16 G. I use these modules to observe the durability of hybrid components, hybrid ready-to-go components under extreme conditions. And this is the schematic of my Hopkinson bar experiment. I placed a specimen at the free end of the incident bar. There is a striker bar. The striker bar hits the incident bar and creates an acceleration in this bar. And I measure the generated stress also, and place the recovery wall to recover the specimen after impact. And the following tests are checked before and after the impact. I did not power the specimen during the impact. I check these tests before and after the impact. As you see, I tried to check almost every peripheral, every feature of the microcontroller and components before and after the impact. And I use a video analysis software, the tracker, for acceleration calculation. As you see, in experiment 1 to 5, the created acceleration is quite same, and created stress is quite same. Because I keep the initial pressure of the striker bar at 3 bar equal in 1 to 5. In experiment 6, I increase the initial pressure of the striker to 6 bar to observe the maximum durability of the components. And as a result of that, in the experiment 6, I reach almost 20,000 G. Now I want to show you the footage of this experiment. In experiment 1, I use this model. This specimen is molded with epoxy cone to hold everything together. And this is the footage of 14,000 G. As you see, nothing happens to specimen.
Jambi, what is the duration of the whole, say, record for
it's
this?
It's about 180 microseconds.
Microseconds, okay.
Yes, it has 180 microseconds. And in experiment 2, I use bare SMD components. As you observe, nothing also happens, but the small reset button moves a little bit. And in experiment 3, I also placed MPU 6050 with plastic screws, and as you see, one of the screws is popped off. And in addition to that, I also damaged some of the leads of the microcontroller, whether it will affect the durability of the microcontroller or not, but it does not affect anything. And in experiment 4, I used THD components, larger and heavier size components. As you see, the MPU 6050 shaken too much, and the capacitors are also moving. This is the only result of the inertia of the components. And in experiment 5, it is identical almost with the experiment 4 because the conditions are same.
Can Bey, are there any similar videos in the literature?
No. Yes. First of all, this is the first footage of the electronic components under thousands of G.
Well, since we have no connections to military, so we are free to
Yes.
publish them, but others, if they are affiliated with military, that's why they are keeping it, undercover. Yes. And this study is unique in that respect, and these videos as well.
Yes. And in experiment 5, I used the specimen 5 again to observe the maximum durability of the components. As you see, the components come to the edge of break-off. You can observe the motion of the MPU 6050 such that, and you can observe the motion of this small resistor like this. This is the only reason of the inertia of the components. And I also want to show you the real specimen. Can you see my specimen here?
Tell me, you need to stop. Yes, now.
Yes. Excuse me. Yes. These are the specimens that I prepared. After impact, I removed some of the epoxy to check the feature of these microcontrollers. And these are the real affected components. And it is very hard to bend this MPU 6050 by hand. In the video, you observe this motion, but as I told you, it is very hard to bend this motion. Now I will continue. This is the table of the functionality check. After the second impact, the specimen 5 failed in all tests, as you see. Interestingly, the specimen 4 also passed all of the tests, but it is very hard to say that the THD components, non-ruggedized components, are suitable for artillery firing, because they first of all they shaken dramatically, and with high probability some of their features are changing because these aluminum foil capacitors has a gap between their plates, and the capacitance of this capacitor with high probability change also.
Exactly, they are working, but we don't know how
Yes.
much of a change in their given capacities, resistances as such.
In the future, the impact, the features of the components can be observed during the impact also. And now I will continue with my case studies. My first case study is a navigation application. The objective of this project is to follow a given magnetic direction. I use a magnetometer and a rotary encoder to determine the distance. And I conduct my experiment in our mechanical engineering building atrium. And I measure the magnetic flux density of each corner of this chessboard at 4th of November 2019. And as you see, the distribution of the magnetic flux density is not equal. Therefore, my car affected. Let me show you the video of this motion. Maybe I have to, yes. Yes, the car follows a given magnetic course and corrects its course when it's course off. But when it comes to the edge of the chessboard, it will distract it from its course, as you see.
Well, John, I think the story is not quite understood at this point. This is one of the earliest experiments, even before a lot of the analyses were made. The idea here is that your missile or your guided projectile would be guided by magnetic field, and not with the GPS and with inertial devices, right?
Yes.
That's the idea, because the enemy could shut down all the GPS-related devices so that we could be blinded. So the idea here is that wherever you want to operate, you generate the magnetic field map of that region, right?
Mm-hmm. This is it was a standalone navigation application.
And then you map that region and you give your say directions based on that map.
Yes.
So that little toy is doing it.
Yes, of course. Yes, I can continue, I think. In my second case study, I study on 6 degree of motion of an aircraft. I used a decommissioned aircraft A7A Corsair 2 as a aerodynamic coefficients. I used optimal control methods in this simulation, and I combined flight gear and MATLAB Simulink together in this simulation again. And this is my complete block diagram for my simulation. I have a also small video for this simulation. I have 3 input: elevator, aileron, and rudder. As you see, when I give the command, the aircraft follows quite well. And when I give the rudder command, it follows again quite well. Now I will apply an elevator input, and it will ascend.
This aeroplane represents what, Canbek?
This actually this is the own motion of the plane. This is the real aerodynamics of this model, and actually it shows that this is the 6 degree of freedom model. When I have the aerodynamic stability derivatives of any munition, the simulation can be also implemented to any guided projectile.
Okay, even though we are seeing a plane, it serves
Yes.
our purpose.
Yes, the same. The purposes are same. If I have the aerodynamic stability derivatives of any munition, the simulation can be replaced. And in my third case study, I studied on analog digital converters. I tested internal and external ADCs. I choose STM32F4, MCP, and ADS external ADCs. These are the features of the ADCs. The MCP is a 12-bit analog digital converter. ADS is a 16-bit, and the resolution of the STM32 can be changed. And I determine a test mission, as you see. I supply an analog signal to ADC and reconvert this converted signal to a analog signal to observe the latency of the conversion. And I keep everything except the ADC same to overcome the non-ADC related errors, issues. As you see, the STM32 is the fastest. Its latency is about 2 microseconds. The other one is around 20 microseconds. This is the sine wave test results of the test mission. As you see, the STM is the far beyond the external ADCs. The signal distort after almost 5 kilohertz. And as you may guess, everything comes with a price. This is the experiment with external and internal ADC. I supply a fixed analog signal and measure the analog signal during a high computational work, and I write some data on SD cards during the analog digital conversion. And as you see, the internal ADC of STM32 has great offset and has lots of noise. On the other hand, the ADS 1115 has quite good values. And the manufacturer of the microcontroller also says that the CPU activity must be minimized during the analog digital conversion to overcome these noise issues. And I think that the error may be caused by the same bus, same peripheral bus, because STIO and analog digital converters uses same APB line. There may be also lots of affecting issues, but I think that some of the reason may be this. And if I conclude my...
Before the conclusions, what do you suggest? What is the moral story of this? These are important concepts.
Yes, of course.
What do you suggest to researchers that are, young people? Some of them left. What I see is that. All right. Well, what do you suggest?
First of all, if you have to make very precise analog digital converters, you have to use external ADC, or you have
standalone ADCs.
Yes, standalone ADC, or you have to convert your analog signal while there is no CPU activity at the same time. If you make analog digital conversion with DMA, and at the same time you have some LED toggling or Bluetooth signal sending, or such that STIO using STIO writing data on the SD card, it may distort your converter signal. You have to use a standalone ADC if you have to make a precise analog digital conversion.
So however expensive experimental boards, those development boards are not good for precision ADCs then, right?
Yes, of course. Yes, I can complete, I think. In my thesis, a navigation model was created, pole placement, healthcare controller, and observable models were formed, and MATLAB Simulink and flight gear softwares combined to create a flight simulation for a guided projectiles. CFD calculations are also carried out, and for lower launch velocities, and durability of commercial off-the-shelf electronic components are studied in an environment that simulates an artillery firing using Hopkinson bar test equipment. And some of the important issues, such as applied navigation system, 6 degree of freedom simulation, and analog digital converters were studied in my thesis. And these are my references for this presentation. Thank you for your listening. If you have any question, I can answer.
Okay.